Hi, I'm Jie Liu. I'm from Department of Computer Science in National Tsinghua University. In this work, we present learning diffusion models for multi-view anomaly detection, which use diffusion model to address multi-view anomaly detection. In anomaly detection, we need to identify which object has an anomaly and find the location of the defect. And all the training data consists of normal samples, and we don't know what the anomalies look like during training. So we use the common approach memory bank method to solve it. We discovered two challenges in anomaly detection. First challenge is traditional multi-model method, usually trains to separate models to extract RGB and 3D features to identify defects. So it is difficult to combine RGB and 3D information together. Another challenge is ambient light reflection can lead the model misidentify the defects in a single image. We can distinguish the anomalies in this object. So we consider multi-view formulation for anomaly detection. Multi-view means each sample has not only one observation. It can be different condition or multi-model. For example, in iCandy's dataset, each sample has 6 images with different lighting condition A to F and the corresponding 3D normal map H. Although we use the multi-view dataset, but the defect may appear in specific view. So we need to integrate these 7 views in one object. Next, I will introduce how to address these challenges. This is our pipeline. In first training stage, we can learn one view agnostic diffusion model to solve RGB and 3D normal map representation problem. In second training stage, we add a control net to our architecture to solve the multi-view integration problem. In inference stage, we build a memory bank from all training features, and we identify defect by using testing feature compared with the most similar normal features to detect the anomalies. To solve the first challenge's multi-models problem, we found diffusion model can solve it. DIFT found that the unique features of diffusion model can gradually learn colors and geometry information of images during the denoising process. Thus, we randomly input all the lighting images or 3D normal map into our view agnostic diffusion model, and we randomly add noise to the latent Z into ZT, and UNet can predict the noise epsilon theta to learn imagery representation. Here, we learn view agnostic diffusion model, we can extract RGB or 3D features to identify defects. We still face how to integrate 7 views. Under the diffusion framework, we additionally use the model name control net. The original paper said control net can use the hint data named condition data to enhance the UNet features and control the contours and style of the generated images. In our architecture, we have 2 phases to train our control net. In the first phases, we use 6 lighting images x1 to x6 as inputs and the 7 view normal map as condition data. We duplicate the normal map into 6 copies to match the number of the lighting images. We input the lighting images into our VAE and add random noise and input into UNet to predict the noise epsilon theta. We also input the condition data normal map into control net. Control net can give the 3D hint to the RGB UNet feature, so our input image learns better representation during the denoising process. Finally, we can obtain the RGB UNet features from each layer. On the other hand, 3D normal map can be used as the input data, while the 6 lighting images can be used as the condition data to extract our 3D feature. The difference between these 2 phases lies in the input data and condition data, but they are trained simultaneously, so we have the RGB and 3D features from each layer to do next things. For training view invariant control net, we have 2 loss functions. The first loss is diffusion loss. We can use the UNet to predict the noise of the 6 input. We aim to reduce images noise by predicting the noise. Diffusion loss can help our UNet feature continuously learn the representation of the input data. Additionally, we use feature consistency loss. For example, using 6 lighting RGB as the input and normal map as condition data, we can get the 6 UNet features, and we can average 6 UNet features to get a mean feature. By the deviation from the mean, we can make the 6 UNet features more similar to their mean feature. This process can be applied at each layer, and we can sum of all the results. Here, we learn the view invariant features mean feature, and this mean feature already eliminates the lighting conditions and make us easy to find defect. In inference stage, we use the same process to obtain the decoder block 1 feature from all training data. We can directly average the feature from the 6th view and use the mean feature as the representative features. We add all the anomaly-free mean features to our memory bank mRGB and mnormal map respectively. During the inference phase, we will use the same process to obtain the mean features. For each feature that may contain anomalies, we search the memory bank for the most similar normal features, and we use the L2 distance from testing features and normal features to compute our score map. And we can find a large difference between anomalous features and the corresponding normal features. So the red areas means there is the greater distance here. Since both score maps are predicted by the same model, we can simply add them together to obtain the final score map. We are the state-of-the-art in icing this dataset. Some defects is not visible in this view, but our model integrates all the information from 7 views. We can find out all of the defects in this object. We also provide a traditional multi-model dataset and VTEX 3D-AD, where our method demonstrated powerful anomaly detection capabilities. This indicates that our method can be widely applied to various scenarios.